General consideration. And mixtures of ideal gas. Let us consider a general mixture of n components each a pure substance so the total mass and the total number of moles are m total and n total number of moles The mixture is usually described by a mass fraction concentration and the mass fraction concentration and mole fraction concentration. Which are related to the molecular mass Mi each M we may then convert from a basis to a mass basis as this ratio. Ci concentration for each component or Ni molecular mass summation of and from a mass basis to a mole basis. For the mole fraction of each component in a mixture. The molecular mass for mixtures become mass for mixture in total which is also used in previous relations. Consider a mixture of two gases, not necessarily ideal gas. Such as that shown in this picture. What properties can be experimentally measured for such a mixture? Certainly we can measure pressure, temperature, volume and mass of the mixture. Pressure, temperature, volume and mass. Of the mixture, pressure, temperature and mass. We can also experimentally measure the composition of the mixture and thus determine the mole and mass fractions. Suppose that this mixture undergoes a process or chemical reaction and we wish to perform a thermodynamic analysis of this process or reaction. uses for process or reactions. What type of thermodynamics data would be used in performing such an analysis? One possibility would be to have tables of thermodynamics properties of mixture. However, the number of mixtures that is possible is regards to both the substance involved and relative amount of each. Is it so great that we would need a library full of tables of thermodynamics properties to handle all possible situations? It would be much simpler if we could determine the thermodynamic properties of mixture from properties of the pure component. This is in essence the approach used in dealing with ideal gases and certain other simplified models of mixtures. One exception to this procedure is the case where a particular mixture is encountered very frequently. The most familiar begin tables and charts of thermodynamics properties of air are available. However, even in this case, it is necessary to define the composition of the air for which the tables are given, because the composition of atmosphere varies with altitude, with the number of pollutants, and with other variables at a given location. The composition of air on which air tables are usually based is as follows. For example, in this chapter, we focus on mixture of ideal gases. We assume that each component is uninfluenced by the presence of the other components and that each component can be treated as an ideal gas. In the case of a real gaseous mixture at higher pressure, this assumption will probably not be accurate because of the nature of interaction between the molecules of the different components. In this book, we will consider only a single model in analyzing gas mixture, namely the Dalton model. Dalton model. Dalton model. For the Dalton model of gas mixture, the properties of each component exist separately and independently at the temperature and the volume of the mixture. And the volume of mixture as shown in the next picture. We further assume that both the gas mixture and the separated components, we have gas mixture and separated component behave as ideal gas mixture relation which are C I sigma equals to Ni on N total, and also we can write N mix Mi is molecular weight, molecular mass. It is consideration for the Dalton model. In general, we would prefer to analyze this gas mixture behavior on a mass basis. However, in this particular case, it is more convenient to use a mole basis, since the gas constant is then the universal gas constant for each component and also for the mixture. Thus, we may write for the mixture this relation. For the ideal gas, according to this picture, for the components P, A, B, and P, B, V, on substitute we can write this relation N PV on RT from this relation equals to PAV on RT plus PBV on RT, and P equals to PA plus PB. Where PA and PB are referred to as partial pressure. Thus, for a mixture of ideal gases, the pressure is the sum of partial pressure of the individual components, where with using the relation we can write PA and PB YBP. This is each partial pressure in the product of partial pressure in the product of that component's mole fraction and the mixture pressure. Mole fractions and mixture pressure. In determining the internal energy, enthalpy and entropy of a mixture of ideal gas, the Danton model proves useful because the assumption is made that each constant behaves as though it occupies the entire volume by itself. Thus, the internal energy, enthalpy, and entropy can be evaluated as the sum of the respective properties of the consistent gaseous at the condition at which the component exists. The mixture for internal energy entropy with the assumption that each component occupy the whole volume we can write this relation for example U equals to M AUA plus MBUB or M CAUA plus CBUB and H MH MA HA plus MB HB MCAUA plus CBUB HB. In these equations, the quantities UA, UB, HA, and HB are the ideal gas properties of the component and the temperature of the mixture. For a process involving a change of temperature, the change in these values are evaluated by one of the three models discussed in the previous section involving either the ideal gas tables and other methods. In a similar manner, these equations, the mixture energy and enthalpy, could be expressed as the sum of component mole fraction and properties per mole. The ideal gas mixture equation of states on a mass basis is ideal gas mixture equation of a state on a mass basis nr and equals to r constant, universal constant. Alternatively, we can write our mix The entropy of an ideal gas mixture is also can be expressed as this relation. It must be emphasized that the component entropies must each be evaluated at the mixture temperature and the corresponding partial pressure of the component in the partial pressure. The component in the mixture. To evaluate this equation for the entropy using the ideal gas entropy expression, let's say that Si consider a process with constant mixture composition between state 1 and state 2, and let us calculate change for the component I for state 1 to state 2. We have this expression S2 minus S1 S0I ln which is equals to 0 plus Cp0I this part. And for each component, 0I ln R we observe here that the expression is very similar to the previous relation for the change state for each fluid flow in chapter 8, that therefore values S0I, T0, P0 are cancelled out, as does the mole fraction. An alternative model is to use the standard entropy function defined before as S R ln P on P0, and for each component in the mixture, Si